So okay, let's show the no-free lunch theorem. Okay, let's see be a subset of our input domain X, of which size is 2n, 2 times n. The main idea of this proof is to show that only half of the data point in C cannot give any information on the remaining half. Okay, it looks like just trivial, but the rigorous proof of this statement is real tricky. So let's see. For this proof, we consider a data generation model and a hypothesis set defined as follows. So we consider this hypothesis set all possible functions from C, the subset C, subset of input domain to 0 or 1. And we denote by a T, capital T, the cardinality of H. So because we are considering all possible functions, the number of possible functions from the set C to 0 or 1 is 2 to the 2n, because the cardinality of C is 2n, and each element of C can have value 0 or 1. Now there are 2 to the 2n number of possible functions. And we denote by f1 by to f capital T the functions in our hypothesis set H. For each hypothesis in H, let di be a distribution over C times 0, 1 defined by di x comma y is equal to 1 over 2m if y is equal to fix. So which means that we will uniformly randomly sample input x from the set C and define the corresponding output label y using the function fi. That is the distribution di. So simply the distribution d, we are considering always dx is equal to 1 over 2m always. So we are using uniformly random sampling for input x, and define the output y based on the corresponding function fi. Right. Then we have this, the LDI, the loss with respect to distribution di. Loss of fi is equal to 0 because all the data points are generated by function fi. Now we will show that for every algorithm A, the expected loss, expected test loss by using ERM rule is n is greater than or equal to 1 over 4, especially for the worst case. So since we have capital T number of data generation model, so we have a capital T different data distribution di. We will have a capital T number of different cases for one given single learning rule. So the learning rule can perform very well to one specific data distribution model di. And this could be very bad for some specific data distribution di. And here we will consider the worst case, the max possible, the expected test error by ERM rule. And we will show that the worst case test error is n least 1/4. So we first construct a training set of n examples from C by 0 and 1 set, which are randomly sampled with replacement. So with replacement means same data can be generated again. Without replacement rule means once one sample generated, then we cannot regenerate the same instance again. Okay, that is the difference between with replacement and without replacement. Anyway, so there are k here k is 2n to the n possible sequence of n example from C, because at each time, so in the previous slide, at each time we have 2n possible instances, and 2n possible instances having distribution having probability 1 over 2m. So from 2n possible instances, we uniformly randomly generate a single training data point. And since we are using with replacement rule, every time we generate a training data point with the same rule. So every time we have 2n different possibility. So and then we repeat the data generation process n times. So there are 2n to the n possible sequences of n examples from C. Okay, so we denote by S1 to Sk all the sequences. We also denote by Sij here to denote the data sequence generated by the sequence Sj, and the corresponding alpha label comes from fi function. So here I denote the function index, and here j denote the sequence index. Okay, right. Then the expected test error is equal to 1 over k times the summation from j1 to k, the test error by the ERM rule or by some running rule A. Okay, right. So this is exactly the definition of this expectation, because we use uniformly random sampling rule. Right, so 1 over k comes from the uniformly random rule, and we are just adding up all possible training sequence and all the output by the algorithm and the corresponding test error. Here we use this very special property, maximum always greater than or equal to the average, and average always greater than or equal to minimum. So we can replace this max by this empirical average, and this empirical average by mean with this relationship. Okay, and we can interchange the order of summation by Fubini rule. So from the previous statement, this and this, it's sufficient to show mean of j 1 over t sum from I1 to k LDI, the rehearse of algorithm output from the training sequence Sij is greater than or equal to 1 over 4. And to show this, it also sufficient to show that every this is greater than or equal to 1/4 for any j. Then the fact every j satisfy this imply minimum of this also greater than or equal to 1/4. So in the remaining part of the proof, we will show that this is greater than or equal to 1/4 for any given j. Okay, so now we fix j, one of value in between 1 to k. And so here let Sj, we simply say Sj is the sequence of input x, and C set minus Sj, okay, so this is set j, the same thing, is equal to V1 to Vp. So since the cardinality of C is 2n, and we randomly sample training data point Sj uniformly and random, and without replacement. So there exists endless n number of non-sampled data point. Okay, so when you compute, when you find the set difference, C set minus Sj, then there are some element, and P is greater than or equal to n. So this is the number of unsampled instances. Then for every function h from C to 0 or 1 and I, we have this loss function LDIH is equal to 1 over 2n summation the indicator function, which value is equal to 1 when hx is not equal to fix. Okay, why this is the test error of hypothesis H? Because the DI distribution randomly sample the input x from 2n set C element uniformly and random, and then the error means the instances our estimated hypothesis H is not equal to the true hypothesis Fi. So here Di means the true hypothesis is Fi. So the test error is exactly this. And this value is greater than or equal to this. So here I just replace this summation by the remaining data point. Okay, so since we use a subset of set C, and this indicator function is non-negative function, or this value is smaller than or equal to this, because the range of summation is less than the previous line, right? So from the definition, we have this, and P is, we know that P is greater than or equal to N. We can replace N by P and have this sign. Okay? Because we are trying to find the lower bound of this. This is good. Right. Therefore, 1 over capital T times this summation is lower bounded by, so when we replace this by the previous inequality, we can replace this by this, right? And again, using Fubini's theorem, we can exchange the order of summation like this. And we know that the average is bigger than minimum. So this is average, so we can replace this sign by mean indicator. with this less than or equal to sign. Okay, so for any given r, from the definition of t function, there are t over 2 functions having the algorithm output is not equal to FIVR. So what is the definition of t function? Capital T functions means all possible functions defined on set S, right? So every single input element have corresponding functions 0, 1 with equal size. Okay, so among capital T function, t over 2 functions having label 1 and t over 2 functions having label 0 for any single given input instance. That is why because we define function, capital T function, that cover all possible pairs. Okay. So from this fact that we can say that this is equal to 1 over 2. When you consider all possible functions, there are half of functions having equal sign. There are half of functions having non-equal sign. Always, with any fi, with any VR, we always have 1/2 for this part, right? So from this, you can say this is always hold. That's it. Okay, let's conclude this theorem. So now we have that every algorithm with n training instances has function f and a distribution d such that, this typo, such that the rows is equal to 0. And the test error, expected test error, is greater than or equal to 1 first. Right. Then from this inequality, we can conclude this theorem. So from the this very simple tree, we can upper bounding the expectation by using the two case. The test error is greater than or equal to 1 over 8, and the other case, the test error is less than or equal to 1 over 8. And since in this case the test error is upper bounded by 1 over 8, 1 over 8 is the last value we can imagine for this case, right? So from which we have this inequality. Okay, so here again, here in this case, when the loss function is greater than or equal to 1 over 8, in that case we have a trivial upper bound, the loss is equal to 1. And in that case, since we are considering the case the loss is less than or equal to 1 over 8, so this is the probability for that case, your loss is less than or equal to 1 over 8. The 1 over 8 is the largest possible loss for this case. So we can simply upper bound the expectation of loss by 1, the trivial upper bound of your loss, times the probability your loss is greater than or equal to 1 over 8, plus 1 over 8 times the probability your test loss is less than or equal to 1 over 8. So when you rearrange this inequality, we finally have this. Our test error is greater than or equal to 1 over 8 with the probability n is 1 over 7. Okay,